Okay, so today I want to start with just reviewing the state pattern that we talked about last time. Very quickly, just about to review how we talk about polymorphism and dynamic binding for the state pattern very quickly. Okay. This is really the most important slides you want to really get yourself into, which is about how you can create a polymorphic collection of states. So you don't really have to duplicate the creation of the object. There's only a single state object for each state over here. Let's just talk about very quickly about the idea about a state design pattern. Remember for this particular lecture last week, we talked about the 3 different designs. So now I'm comparing number 2 and number 3. Okay, over here, let's say we have basically either the top-down non-OO solution versus the OO solution over here. Well, without diving too many details, since we covered that already, I want to point out to you the fundamental difference over here. You can see for the top-down approach, we actually got the current states explicitly encoded as an integer value over here. And then to really execute the session, you always have to explicitly pass an input parameter called current states. So that's the main, let's say, drawback, because it will eventually violate the single choice principle as we talked about last time. You can review to the lecture recording from last week. And then on the other hand, if you go for the object-oriented solution, in that case, what you will get is the current states is going to be of the type states over here. So you can think about the state here is going to be the top of some inheritance hierarchy, which we'll see in the next slides. And then now, in order to execute feature whose behavior should be specific to a particular state, you can now make use of dynamic binding. So depending on what the dynamic type is for the current states, you're going to actually give you the behavior accordingly, okay, according to the dynamic type. That's a very quick review on the state pattern. And of course, you should also make sure you review the hierarchy, the design hierarchy for the state pattern very quickly. So you have at the top level here, the state defer class over here, and then you have the all the descending classes that are effective, which means they implement all the features. So you got initial, you got help, final, and etc. How many descending classes you need depends on how complicated your state diagram is over here. It really depends. But in our example, we only got 6 states. I would say realistically, you might easily get up to maybe 100 or even 1,000 states. It really depends. And then we talk about how the dynamic binding is going to work for different features, right? We talked about it last time. And one more thing to point out to you. You can see in the state class, the only feature that is actually implemented is called the execute feature. And we said that this is considered as a template, which we'll review also very quickly in the next slides. The template is called execute, which means inside the template, we're going to actually refer to defer features. And those defer features will be implemented in each of the descendant classes over here in the cluster. Okay, you can see all the features over here. On the other hand, they are all deferred. Okay, let's see one more review over here before we talk about something new from last time. You can see in the state class, which itself is deferred. And we got this particular execute feature. You can see that one there is implemented. So now you got a do and body here. So that's implemented. However, the way you implement it is by referring to defer feature. For example, you can see the display feature over here is now referring to the display in the same class. But that one is deferred, right? So this is a very interesting pattern that you really want to get used to when you review the state design pattern. And if you refer to the notes from last time, we also talked about when you try to execute these lines of code, how dynamic binding is actually going to work to actually let you call the corresponding version of the execute and also call the corresponding version of display, read, and etc. Okay, so these are something we covered last time. Okay, so I'll pause a little bit. Anyone have questions? Okay, hopefully so far so good. And of course, again, if you got questions, please just raise your hand or just type to me. I can also see from another monitor. Okay, let me continue with the stuff here. So today, the first part for the lecture, I would like to finish the state design pattern by just going through one test case very quickly so you can see how everything works together. We briefly touched upon that last Wednesday, but let's be precise this time. Let me go back to the slides over here. Again, that's a polymorphic array that we talk about. And then let's see the application class. You can think about this is the overall clients who is going to make use of the implemented state design pattern. But how do we do that? Okay, let's just go over it very quickly, and then I will point out some important lines as we go there. Okay, let's say we got a class called application, the clients. And then we got basically two important features over here. So these are the two attributes. The number one is a transition table, which is a two-dimensional array. And it looks like this, okay, for the transition. The transition basically looks like this guy here. Okay, let me just show you the diagram here. You can see for the application, the clients, we have transition, which is a two-dimensional array of integer. So now you can see this is a two-dimensional array that we have over here to implement the transition table, right? For example, you can see over here, if I'm currently in state number 2, and now I want to take action number 3, I should end up in state number 3. So this corresponds to, you can see I'm currently 2 over here, and then I take action number 3, I should end up in state number 3, right? You can see the correspondence for each encoding here. Okay, that's about the transition. And also we got another variable over here. It's called states. So this is so-called a polymorphic array or polymorphic collection of states. Dynamically, we can actually create for each index here. You can see for states. Okay. So what you should note about is states at any position I, where I would be the valid index over here. So I would be of static type will simply just be states, because it's what we declare that to be. What about the dynamic type? Dynamic type for states of I can be any of the descendant classes of the state class. Okay, I'll just say descendants. For example, you can see initial here, you see fly inquiry, see inquiry, and etc. Right? But in this particular case, since we got 6 different states, so that's why the size of the array will be simply 6. Okay. Let me switch back to my slides over here. And we'll see exactly how we can manipulate the states in just one moment. And we have some initial value over here. You can think about the way we refer to the states right now is by telling what's the index of the states objects in the polymorphic array. We'll see how to manipulate that in just a moment. Okay, we got a number of states, and also we got a number of choices depending on your application. And also we got the make feature, which will just initialize everything, right? That one there, I don't need to waste your time. And also we got invariants. So this will be some interesting invariant to write just to make sure everything is within the constraint. Okay, for this one, let me just tell you directly before I take questions later. Okay, you can simply say transition the height and transition the width. When you say transition the height, it's telling you how high the table is, basically the number of rows of your two-dimensional table. When you say transition the width, it's going to be how many columns you have in the table. So that'll be just how many columns, right? Okay, not too bad. And then we're going to the same class. Let's see, also you can try to put states into your array. For example, over here, let's say over here, I may want to put maybe in index number 2, I want to put fly inquiry objects in there, right? You can see the more details in the coding. Okay, I also made the source code available to you. Also, you can choose the initial state to be a certain state, let's say index 1. And also put transition. I want to just, for this particular example, when you review, notice that we chose a particular order for the input parameters. We say that if you want to put in some transition, put the target state first, and then the source state, and then the choice. So what do I mean by that? Let me just give you one very simple example. If you go back to this particular diagram over here, let's say we are interested in putting, let's say, this particular input. Let's say I'm currently in state number 1. If I take action number 2, I will end up in state number 5. Let's say that's what I want to encode into the transition table. What I need to do is like this. I would say put transition. And now the order of the integer will be very important, right? Because now the target states will be 5. So now I'll put 5 over here, first of all. And then I'll put the source states, which is 1, and then followed by the action, which is 2. Okay, that's just the order. You have to be consistent. Of course, for your particular design, you might actually choose to put any order you like. But for this particular example that we talk about in the lecture, you'll put the target states, the source states, and then the choice. Okay, and then you may have some precondition here. Just make sure the source, target states, and also the choice, they are all valid. Okay, and put the table here. Okay, and okay, I'll pause a little bit here. Is there anywhere you would like some more explanation here? If you want to raise your hands. Okay. All right, very good. So now let me just talk about the final bits about this particular state pattern. So final bits, I also briefly talk about it. So the final bit will just be a running test case to show you how everything works together. Okay, let's trace them very carefully. I'll go through the slides in animation very quickly, and then I'll switch to iPad to show you the runtime behavior, which is more important. When we're going to declare application, we're going to declare current states, and notice that the current state is states over here, right? Compare this with how you would declare current states in the non-OO approach, which would be integer, right? And the index over here is going to be the index into the polymorphic collection of the array, right? And then we're going to see how we can change the index over here throughout the code, and we'll change the current states accordingly. I'll show you how to do that. Okay, we got to create some application, and then we're going to put the states. And now let's say initially we simply we're going to put basically 6 different states, because you can see what we want to put eventually. We're going to put initial, flight inquiry, sea inquiry, reservation, etc. We're going to put 6 of them. So now this one only shows you just a single line. And we'll just say similarly for other 5 states, right? That part is easy. I don't need to show you animation. And then we can also say I want the initial state to be index 1. So which means I want the initial object over here to represent the initial state of my system. Okay, it doesn't have to be index 1. Just for this application, it happens to be index 1. And then I'm going to go on, and then for put transition, right? That's something I just talked about previously, right? So this was the example I talked about. You can imagine that in order for you to set up the transition table, you had to put in this guy here, this guy here, this guy's here, and etc. Everything. You can think about whatever you left is 0 over here, which means the corresponding transition is undefined. Okay. Let me go back here, and that's about put transition. Now, what I want to now do is to show you exactly how the current states being of state type is going to be manipulated. Okay, let me switch to iPad right now. Okay, everything up to here is not too bad. You just have to see the details when you do the coding. Let's see this one first. If I look at this line over here, I'm basically saying index over here is going to be assigned to application.initial. Remember, I chose initial to be simply just 1, right? So that means the index over here will just be reassigned to 1. Okay, that one's straightforward. And now let's see how the current state is going to be changed accordingly. For the current state over here, we'll simply say current states. Let me just write it here. You can think about the current states over here. It was declared to be of static type states. So I will put it here. Statically, it's current states, right? Statically, it's a state. Dynamically, it can be any of the descendant classes of the states, which can be, if you refer to the hierarchy over here, it can be any one of these, right? The descendant classes, okay? Just as a reminder. So now, if I go back here, initially, we say current states is simply assigned to index 1, right? Index 1 of the states array. So application.states is referring to this particular array. I want to go to index 1, which is this particular initial state. So that means current states is now going to point to this particular object. So this is the current layout. Okay. Oh, so the audio, right? Yeah, I'm afraid that could be either the network, either from my side or from your side. Yes, that could be maybe something we cannot really fix right away. But again, I think the recording after I finish the lecture will be made available to you as well. Maybe try to follow as much as I can. I do apologize for whatever sound quality compromise, right? Anyway, we'll do our best. Okay. All right, so now let's say for the current states, for now, it's simply referring to the initial states. Let's see how we can modify that quickly, okay? The idea would be, so of course, over here, you can think about we're simply checking to see the current states, the dynamic type is indeed initial. So we talk about the check as the attach expression when we talk about the cast. It's more like an instance of check. We're trying to make sure current states currently is instance of initial indeed, because it is pointing to the initial states. Let's go a little bit further. Okay, let me change my pen color here. So now let's say this. Let's say we want to make some transition, and the way we make the transition goes like this. We're gonna reassign the index over here, which is gonna affect the current state. Before that, let's see the right-hand side of the assignments. So let's now look up the transition table over here, and then the current state is actually 1, right? The current state is simply just 1. And then we want to say, we want to take action number 3. Over here, the corresponding state should just be 2 over here. So the index will be reassigned to 2. Let me just tell you conceptually, this is what we are trying to do. We are now currently in index 1 over here, which is here. And then we are trying to take action number 3, which is by taking this particular transition, we will now end up in state number 2, right? That's exactly what we're doing conceptually. So now, the index will just be 2. So now we can say the current state is now going to be reassigned to a different dynamic type objects. So now application that states the same polymorphic array, so now index will just be 2. So that means what we're doing is current state, rather than pointing to index 1, it is now going to point to the index 2 states objects. Index 2 is over here, is pointing to this flight inquiry objects. So that means current state is also going to point there. Okay, so hopefully you can see how we can easily change the dynamic type for the current states. Okay, one more thing to actually tell you, right? So now, let me just add 2 lines of code just to illustrate to you why dynamic type is so important. Let's say over here, let's say right after, let me just highlight the 2 lines I want to show you. Okay, can we just look at number 1, this line over here, and number 2, this line over here. Okay, so now the 2 orange lines I just highlighted. Now we want to see what will be the consequence for each one of them. We want to see. Okay, so what I can do is I can simply go to, let's say use purple. Okay, immediately after this orange line here, the first one, if I say, I'll say CS for current states. If I say current state dot display, for example, right? If you remember in the architecture over there, we talk about every state object supports read, display, correct, process, and message. I'm just making one example by saying, let's say display. I'll just choose one of them to show you dynamic binding. And what I will do now is I'm going to say CS.display. That's number 1. And then for the second orange line over here, you can see the second one, right? Current state is reassigned. Immediately after this, if I say CS.display. So now the question is, which version are we going to call for the both display? If I call this 1, if I call this 2, okay, what should be the version of display that's going to be called, right? I'll pause a little bit for you to think about. You don't need to answer me. Okay, just pause just a few seconds. Think about which version of display is going to be called over here, and which version of display is going to be called here. Okay, the hints will be, you may want to consider dynamic type. Since now we are not talking about compilation, we are talking about runtime behavior. Okay, let me tell you what the answer is. Okay, so now for the first one, because we know the dynamic type after this particular reassignment is going to be initial. So now after 1 is going to call the version in initial. Okay, that's the version from initial. And for number 2 over here, because now we are immediately after this particular assignment over here, dynamic type will be flight inquiry. So that means for number 2, we're going to call the version of display from flight inquiry. Okay, hopefully you can see that, right? We briefly touched upon this as well last Wednesday, but now it's more thorough go through of the code. Okay, so now I would like to just talk about a little bit more. So now if you go a little bit further here for the slides, you can see So this is a top level for how you can implement execute session from the clients. This one is pretty much the same. So now, rather than just having like a manual encoding for the current state, you can say do the transition like a one at a time. Now we can have a loop to actually do the transition, to say we are gonna keep doing transition until the user actually wants to log out, for example, right? So this one I'll show you quickly just for completeness. So now again, we got the same setup with we got current states, we got index. Now the way we're gonna see the loop is gonna automate is a pattern that'll be very similar to what we just said before. Current state will always be reassigned to something else according to some transition. Okay, that's exactly what you will see. Okay, the test case I just went through is just one iteration if you want. Okay. Okay, so now we're gonna say from the index being the initial, so always the system start with the initial states, and then we say until we are reaching the final state. Maybe the user has paid and now they are ready to log out, and then we say the current state is always assigned to the current index value, right? So the reason I say it's polymorphism is because you can think about, okay, let me just ask you this again. Let me just go back here. When I say polymorphism, it's more about compilation over here. Again, you can think about it does it really compile? Right, you want to think about for this particular line. Okay, let me just tell you very quickly. In order to decide whether you should compile or not, you should consider the static type for both sides. For the right-hand side, the static type is simply what you declare the states array to be, right? You can see the states array. Every member over there has a static type states. So that should be states. And then the current states was also declared to be of static type, also states. The static type over here is also states. So all you got to decide is state is a descendant class of itself, right? So now that will compile. Now dynamic binding is actually go a little bit further by saying at the runtime, as we illustrated in the previous page, the current state over here may be pointing to the initial, or it may be pointing to flight inquiry, or it might be pointing to any of the other states dynamically. So that means when you try to execute this particular line to say current states dot execute, okay? So now what you want to really be able to answer to really show your understanding for this particular design pattern is by saying, here's my question. How does this particular line illustrate dynamic binding? Okay, so what you want to say is dynamic binding is illustrated in this line because depending on the dynamic type of current states, the corresponding version of execute will be called. And let's go just a little bit further to it. Remember we said last time there was only one version of the execute feature, right? There's only the execute here, which was the template. However, if you want to trace thoroughly, you can see when you are tracing the execute feature line by line, you will actually see that the first one will be display, which again depends on what the dynamic type is. If the current dynamic type is simply, for example, C inquiry, you're going to call C inquiry version for the display. If the current dynamic type is confirmation, you're going to call that version for display. Okay, so everything actually connects from the last lecture. Okay, I'm not going to waste your time on this. You can refer to the lecture recording, or you can ask me later. Okay, so there's only a final thing I want to say about the state pattern, and then I'll pause if you got any questions you want me to review. Okay. All right, let's take a look. So we got interactive section here. So now this slide here just basically summarizes for you as a client how you are supposed to use the state design pattern. So every little detail is summarized over here. You can refer to it, but we cover every one of them already. Okay, so now this is a final slide to summarize really design number 2 and also design number 3. So I would say start with this slide when you study for the pattern. In the top-down hierarchical solution, design number 2, we have to, whenever, let's say display, we have to explicitly pass the current state being integer. So that's why you're going to say display 1 and display 2. You can see the explicit state number over there, right? 1 and 2 here are simply state numbers. On the other hand, for the OO solution, we can think about we basically hide the state encoding over here into the current dynamic type of the states. That's it. That's basically what we're doing. So you can simply declare S to be of type states rather than integer. And then, depending on what the dynamic type is, when you say S.display, it's going to call that corresponding version. Okay. So this slide here is really important to really check your understanding for the state design pattern compared with the non-OO approach. Okay, so that's about for the state design pattern. That'll be the first part for the lecture today. Okay, maybe I have talked too much. So do you have any questions? Anyone? I can see we got 53 online right now, which is pretty good. Okay, if you got any questions, if you want to speak up, please either raise your hand or you can just send me a chat message. Either way. Anyone? Okay, I can still wait for a little while, okay, before I switch to the next topic. Okay, good. Since hopefully everybody's reasonably happy, again, I do apologize if your network connection is not receiving my voice or quality image so well, but let's do our best. Oh, let me see this. I see a question here from John. Let me read it out. Just to clarify, polymorphism, the right-hand side static type must be a descendant class of the left-hand side. Yes, correct. So let me just clarify that to write it out. Okay. Again, you see, what we're learning in this course, even though the working language is IFO, but the principle we learned about OO, polymorphism, dynamic binding, they apply to any OO language you may have to use later. Okay. So what John's question goes like this. We'll just summarize what he said, which is totally correct. Let's say this. When you talk about polymorphism, okay. So basically, let's say if you talk about an assignment over here, you have the left-hand side, you have the right-hand side. Let's make the case a little bit easier, just single variable. If you have variable number 1, and also you got variable number 2. Another question is, does it compile? In order to decide, make a decision on this, you have to check to see what's the static type for V2. Okay, first of all, check that. Let's say, for example, maybe simply class C2, okay, let's say. And also, you have to find out what the static type is for V1, okay? Also, what's the static type over here? Let's say C1. Okay, C1 versus C2. They may be the same, they might be different. The interesting case is when C1 and C2, the two static types, are simply different, okay? Let's say, in that case, what I would do is I'll simply draw an inheritance hierarchy over here. Okay, let's say over here, let's say this is some inheritance hierarchy. Okay, over here. So what would be the valid case? The valid case, the case where the line of code will actually compile is when C2 is actually a descendant of C1. A descendant of C1. If you look at the diagram over here, think about C2 is over here, somewhere in the hierarchy, and C1 is actually over here, for example. That's what you can think about, right? You can see C2 is strictly lower than C1. So C2 is one of the descendants of C1, okay? What's really so important, if you refer to our review lecture on the inheritance, I keep emphasizing, in C2, in this case, the expectation of C2 as much as what C1, its ancestor, can support. Okay, so this is really important because we know C2 can support at least as many features that you may call on C1. That's why C2 can appear on the right-hand side to be the substitution. Okay, it's a very quick summary to what John just said. And there's another question here. Okay, give me just one moment. Will this video session also be uploaded to YouTube? Yes, I'm also recording at the same time. Yep, so you're welcome to stay on if you wish. But anyway, I'm going to record a video for sure. Going to post the video. Okay, another question from Atto. So can you give me a practical example of when the state design is a good approach to solving a problem? I would say the practical example would be if you, okay, I tell you what a practical example could be. Okay, let me first of all go back to my slides. If you go back to the example where the motivating problem, right? So remember, every time before the design pattern, we talk about some motivating problem. What kind of problem can better be solved by this particular pattern? And for state pattern, the practical example would be any interactive system. Any system where the user is going to interact with the system. Okay, let me just give you a little bit conceptual view over here. Okay, you can think about if this is the user over here, and if you think about this is the system. One analogy for you would be if you try to think about your lab number 3 and lab number 4, you have your ETF project, right? Okay, in that case, when you actually run your ETF project in the -I interactive mode, in some way you're turning your ETF system into an interactive system. In that case, your system might be in different states. Okay, that's one example, right? But it doesn't really mean you have to use the state pattern for your ETF project, not necessarily. It depends on the particular example we are talking about, right? So when I say interactive system, the user might send some request to the system, and the system will return some feedback to the user. It could be that the input you just enter was simply invalid, so now you enter again. And the user, again, can also send another request, and the system can send another feedback. So this kind of process goes on and on and on. And state pattern will be very useful if somehow internally the system somehow has to maintain certain states over here to say maybe if the user is currently in this particular state, if they want to confirm, in that case they will go to just another state, and for that particular state you got another set of behavior. So I'll just make it a little bit general for you. I would say every time if your system is such that you're going to interact with the user, and then for your system internally, you might just go from one situation to another situation. In that case, it would be a state pattern. Okay, but of course, you will see that I also gave you not just the online booking system. I think I said over here, I also gave you some more example here, Taobao, eBay, or Amazon, right? So these system over here was something similar to them. You can also use a state pattern. Okay. All right, good. All right, let's, okay, if everybody is happy, let's now move on to the composite design pattern, right? We're actually going to talk about 2 design patterns today for the second half of the lecture. But I will start with the composite design pattern. I want to cover that thoroughly first. And then the next one will be the most interesting one for the course, which is called visitor. But let's see how much we can go through for the composite. Let's again talk about motivating problem for the design pattern. Okay, let me read it to you. Okay, there are many manufactured systems such as computer systems or stereo system. For example, if you go to Canada Computers, right, they basically sell hardware over there. You can assemble the hardware yourself for your computer, or you can order things online. But we'll talk about individual components. So each computer system are composed of individual components and also subsystems. I'll talk about what subsystem really mean in just a moment. But as we go through the motivating problem here, I would like you to think about back in your 2011, the data structure course. Think about what data structure really maps the problem that we are talking about over here. Think about it and I'll give you the answer. Okay. So a computer system is composed of, different components. Let's say what, for example, right? Individual pieces of equipment. It can be hard drives. It can be CD-ROM. I'm not sure you have seen it. Maybe DVD-ROM or any hard drive, basically. Okay, just basic components. So the characteristic for individual piece of equipment will be they do not contain any further other components. Okay, they're more like a base, basically, base cases. And then they might have some properties for individual components. For example, you may want to say how much power the hard drive might consume and also how much a hard drive might cost, right? You only got cost or price for individual components. And then the more interesting case when you talk about subsystems or components that contain other components, that's an interesting case. Composites, we either say subsystem or we might say composites, okay? So composites such as cabinets, like a shelf, and also got buses, like a cable to connect different components. Also, you got chassis. In this case, also like a a box inside your computer box. Okay, so now we got two types of things over here. Okay, so this will be the example we're going to use as a running example for the composite pattern. Okay, it's a little bit old style example, but hopefully it can illustrate the ideas. Okay, and then I will switch to iPad in just a moment by asking you questions, and they'll present some alternative design. Each cabinet, for example, contains various types of chassis, and each of which in turn contains components, etc. Right? I'll show you a picture in just one moment. Now, let's say this is your design task. You want to design a system that will allow us to easily build system, to assemble. Maybe inside a cabinet, you have another cabinet. Inside that particular cabinet, you might have a hard drive, right? Something like that. Let's say you want to build a system as a complicated structure, and also you can calculate the total cost and power assumption. Let's say for this particular lecture, we're going to focus on the cost, the price, let's say. And for power assumption will be something very similar. Okay, and then let's say this. Before that, let me say this. Can any one of you, based on what I have just said so far, a little bit incomplete, but hopefully that's enough for you to take a little bit connection. Back in your 2011, what data structure would you use to implement system within subsystem? Ah, that's good. Okay, so now I got somebody here, Broderick. So if I pronounce your name wrong, sorry about that. So Broderick said it should be a tree. I agree with you. Specifically, you should notice that as a reality check, should it be a tree or should it be a graph? Right? Because in some way, tree is like a special case for graph. Tree is basically a graph without any cycles. So now you want to think about whether a graph will be a suitable conceptual model for this particular motivating problem. I'll leave that thinking to you. Okay, it turns out tree will be suitable for this particular structure, but maybe not graph. Okay, keyword cycle. Okay, think about it. Okay, I'll give you one more example over here, and then we're going to think about what kind of design we can actually use. Let's say this is one particular design example here. Okay, you can see at the top level here, we got cabinets. Oh, think about what we're having over here is like a runtime structure. At the runtime, we can build any particular manufacturing system or any particular computer lab that we wish. Let's say we got cabinet here at the top level. The cabinet contains two chassis over here. The first chassis contains one card and one hard drive. Okay, and also the second chassis contains a single hard drive and also a DVD ROM. And also the third component in the cabinet is a power supply. Okay, apparently you can see it's a tree. Cannot be a graph because if you have a cycle there in the graph, it wouldn't make any reality sense. Okay, that's about a tree structure for this particular problem over here. Okay, so hopefully everybody's understanding about what the problem is we want to support. We want to support a system which can be built by subsystems, and the subsystem eventually can get to the leaves over here, which means you have no further branches. In which case, you can think about power supply, DVD, CD-ROM. They are like leaves over here, and then for more like a recursive case, right? Like a chassis and also cabinets. They are like internal nodes in your 2011 terminology, right? Okay, so now what I would like to do now is to say what the challenge is. When you actually design your classes using, let's say, Bond diagram, to draw your design, client supplier, inheritance hierarchy, I don't know, so whatever that's appropriate. You have to make sure your design can really appropriately accommodate both the basic and also recursive modeling artifacts in this case. That's the main criterion that we want to satisfy. Okay. So what I would do now is, let me just move my slides over here. Okay, so now just bear with me. Okay. What I would do now is to talk about the composite. And before we talk about the composite, there's one new modeling concept that we need, which is called multiple inheritance. And we're going to need that in order to do the composite pattern appropriately. Okay, let's talk about very quickly multiple inheritance. I'll just talk about them using example. Okay, in your previous Java course, you have very limited notion about multiple inheritance. Let me just summarize to you quickly. Okay, let me just go to iPad over here. So now in Java, okay. So when we talk about multiple inheritance, it's only limited to interfaces. Limited to interfaces. So for example, you might have interface number 1, you may have interface number 2, and then you may have some class called C. You can say C implements I1 and also C implements I2. But remember interfaces, so these are interface, right? So interfaces in Java, they actually do not contain any implementation, okay? So it's not exactly kind of the inheritance that we spoke about, because when we spoke about inheritance, we really want code reuse. But when you say you actually implement multiple interfaces in Java, you're only inheriting headers or signatures, okay? Only headers are inherited. So on the other hand, let's say you try in Java, let's say I have class number 1, I have class number 2. Let's say I really want to somehow inherit features from these two classes. Somehow C1 and C2, they are not the same class for cohesion reason, because somehow C1 and C2, they belong to different concepts over here, right? And now, if I just want to have a class C over here, in Java, if I say C extends C1 and also C extends C2, conceptually, I just want to reuse all the implemented methods from C1 and C2. However, this would not even compile because it's a class C extends. Here it says C1 and C2. This is simply not allowed in Java, right? When you want to extend a particular class, only a single class you can extend. However, when you implement from interfaces, you can implement from multiple interfaces. But since we are now talking about design, so from the design point of view, you actually may want to be able to extend from multiple classes and reuse their code. We'll see that, okay? There will be some need for this. Anyway, let's switch to our context over here, and I'll give you an example. So the first example would be as part of the library API for IFO. So we have for numbers over here. Okay, you can see there's multiple inheritance. I will go over that with you quickly. Okay, for example, you can see this. At the top level, we have comparable. You have seen this in lab 1 already for your outgoing sorted. And also you got the numerical class, which is also deferred. We got two deferred classes. Apparently comparable and also numerical, they are not in the same class. They are not collapsed into a single class because they belong to different concepts over here, right? For cohesion reason. Okay, comparable is anything about comparison, right? Like a greater than, right? And also for numerical, it's more like a plus, minus, etc. It's more about arithmetic operations. So they are not the same class. And however, you can see there are descendant classes which might inherit from both of them or either one of them. For example, you can see for the string class is actually a comparable, but it's not a numeric, right? Which makes sense. You should not really be able to say plus and minus on the string. On the other hand, you can see for complex number. Complex number is actually numeric, but you don't really want to compare them using larger than, right? Mathematically, it wouldn't make sense. On the other hand, there are certain classes like an integer, real number, and double. For these three classes, for example, you want to support both the comparison and also you want to support arithmetic on them. So that's why you want to say for an integer, for example, you're going to say inherits from comparable, and also you want to say inherits from numeric. So that's something we will allow in IFO. However, as I will mention later, when you want to inherit from multiple classes, you want to watch out for name clashes. Because, for example, if I declare already f in the comparable class, I declare another feature name which is also called f. But now, which version of f is going to be inherited into integer, for example, right? That's some kind of name clashes you have to resolve before you can start using multiple inheritance. But it's quite a nice modeling feature, so you shouldn't really give it up. Okay, but I would say later on for your projects, you should really consider to see if the multiple inheritance concept can be applied. Okay, think about it. Okay, that'll be the first example I want to talk about for multiple inheritance. And the next one here, okay, let's think about this example here, right? So that'll be the second example for multiple inheritance, and in some way, it would be very similar to the composite pattern that we're going to talk about later, but in an abstract way. Okay, let me tell you what the problem is. I'll give you a little bit of time to think about it. Okay. So the problem is we are going to design windows. Okay, you can think about the blue window over here is contained within the yellow window over here, and this yellow window here is also contained within this yellow window here. And the biggest yellow window here contains so many other windows inside, right? So you have more or less like a hierarchy over here for windows. Okay. So now, and for each window, you also got different properties, right? Like how wide it is, also how high it is, etc. So now, here is my question for you, design problem. Okay. How do you design the classes for such nested windows, right? So let me just give you a little bit of hints to restrict your thinking a little bit, okay? To also make you more focused for coming up with your solution. Let's say we want to support all these features for individual window. For example, height, width, the position for x coordinates, the position for y coordinates. Let's say, for example, you can see this starting point for this window here is x maybe 2 and y 3, for example, just whatever position it is. Also, you may want to change the width, you may want to change the heights, and also you may want to move the window as well, right? You may want to decide to move this blue window here outside the yellow window. And then also you got to support the more hierarchical features, like a parent window. For example, you can see for the green window here, its parents is basically the yellow window here, right? It's actually contained within the yellow window. Similarly, you can think about this particular orange window here. How many ancestors does it have? You can see the immediate parents will just be the green one here, right? You can see the orange one is immediately contained within the green. And the green also immediately contained within the blue. And the blue immediately contained within the yellow. So the yellow, the blue, and the green, they are all ancestors for the orange one. Okay, you can see the idea. And then also we can talk about descendants windows. You can see the yellow one here, the biggest one, contains every other window, including itself as its descendants, right? But let's say now we don't really include the itself, right? And also you can also add child windows into your window, right? So these are the properties that you may want to consider when you design your classes, right? One choice for you to account for all these classes is to put every one of them into a single class, basically, right? So one choice would be, let's say you have a single class, okay, over here. If you decide to simply have a window class window, okay, and then you simply put, let's say for feature over here, I will simply put, for example, x position, also y position. Let me just omit the types just for clarity, just for now, okay? And also x position, y position, and also it could be maybe the width, and also the heights over here. You might have another feature section over here, and then maybe you talk about the move, and also you talk about add some child window, right? Also, you talk about parents or ancestor. Also, you talk about children or descendants, right? So if you put every feature in this particular window, okay? So now this will be our design attempt number 1. Apparently, we are not making use of any inheritance because we're not really reusing the code for any other class. We're saying for the current class code window, we simply put all the features over here, right? So now, I can argue that there is one design principle that's actually violated, okay? I wonder if any one of you know which design principle I'm violating, okay? Without giving you many hints. Anyone? Want to give it a try? Anyone want to try to type? Singleton, You meant single choice principle, I suppose, right? So singleton, by the way, singleton is actually a design pattern. That's okay. That's okay. It's good that you try. Let's say single choice principle. Maybe that's what you meant. Let's think about this. The answer would be actually no, because when you talk about single choice principle, you're really saying there are certain duplicates of the feature over here. So if there are several, if there are two features, they're actually doing the same thing. So that means they're duplicating the same functionality. But you see, X position is definitely different from Y position, and move is definitely different from height. So you can see pairwise. So these are simply just different, right? Okay, so single choice principle is not the way to go. Okay, I got another one of you. Okay, it's cohesion. Okay, that's interesting. I'll write it down first. Another one is called cohesion. Looks promising to me, but let's see what the explanation was. It's cohesion by including the parents and the children. Okay, you're saying that violated because you include both parents and children over here. Are included in the same class. Okay, let's talk about this thinking here. Okay, what I will argue is like this. When you say cohesion is actually violated by this so-called Superman class. Okay, let me write it down. So this is so-called Superman class. It is called Superman class because basically you're trying to put things that are kind of unrelated in a single class. So that means your class size gets very big. Okay, it's a Superman class. I would say this part here, when you say cohesion is violated, I'd absolutely agree. However, the justification is not quite what you're saying. I tell you why. Because when you say parents and children are included, so somehow parents and children are basically to say, let's say this. If I have this over here, if I have the, let me just give you one example here. Let's say I have the pink window here. I got another blue, and also I got another, let's say, green over here. Okay, let's say this is my nested window over here. The way to think about it as a tree, like a nested, is like this. You can think about the pink window over here is like the parents for both the green and also the blue. Right? So the blue over here and also the green over here. That's how you can think of it, right? So these are being the children. However, when you say parents and children, they are just relative notation. You can say the green has the pink as the parents. And also you can say the pink actually got the blue and green as the children. So they are really talking about the similar stuff, right? With consistent notion. So they are not really like distinct concepts over here being included. So I would say we do violate cohesion by having this particular window Superman class, but the reason that it violates cohesion is not because the parents and children are in the same class. Okay. Anyway, so why does it violate cohesion? Okay. The reason is, let me just go back here. Okay. So I can give you the complete list. I will argue the following: when you talk about the height, width, x position, y position, all the way to, I would say maybe all the way to heights. So these are really the features relative to individual window. You just talk about their dimension and how you can change the dimension. On the other hand, when you talk about like a parent window, descendant window, and edge-out window, these belong to another category, which is more about the tree structure of your window, like the one I just talked about over here. Okay, over here. Okay, so what I'm trying to say is, it would be very nice to decompose this particular window class into two classes, somehow related, of course. So maybe one class will be about the dimension for the window. Dimension of the window. Yeah, another one would be about a tree operation of the window. Okay, I'll give you more details. I'm just trying to sketch the idea together with you. Okay, so now we want to somehow decompose this particular window Superman class into group number 1. They should be put into here, and also maybe group number 2. They should be put into here, into two separate classes. But now, how can we actually put into two classes over here and maybe sharing some common code over there? right? That's a question. So now the answer will be multiple inheritance, right? So now let's see exactly how to work out this example here. So we want multiple inheritance. So what we try to do is we're going to make one superclass that's going to be responsible for the dimension for the window. We're going to create another superclass that's going to be responsible for the tree operation for your window. And then for our window class, sorry, I'm running out of space. For our window class, let's say somewhere here. For your window class, is going to inherit from both of them. Okay, that's how we're gonna work out the design. Okay, let's just go over that very quickly. Okay, and then I'm gonna, once we have done that, we can then switch to the composite. Okay, very quickly. So the idea will be to separate between graphical feature like an X position, Y position, and hierarchical tree operations, right? So what we'll do is, let's talk about one class just called a rectangle. You can think about windows like a rectangle. You got all the width, height, X position, Y position, also change the width and change the height, and also move, for example. Let's say that's the rectangle class. So this is one category of features that are coherent. We got another category of feature that will be also coherent, but independent from the rectangle here, right? They are orthogonal, they are different. So now let's say we got another class called tree, and we just make it generic, which means what you store inside the window can be different. It can be string, it can be anything, okay? And also we just say descendants over here, there's only the single query. Like you can also make an ancestor as a query. And then we say iterable, right? Remember we talked about iterable. And we say code to the interface, but not to the implementation. So we say iterable as opposed to array or linked list. Okay, think about that design principle we talked about previously. And then we also got the add over here to add a single child. Okay. Okay, I will pause a little bit over here. Okay, you know what? Let me just say one more thing before I take your question if you have any. Let's say we got these two classes over here, rectangle and tree, right? They have nothing to do with each other because they are responsible for different aspects for the window. And now when we got our final class that we want to define called window. So here we simply say window. So this will be the syntax you have to write if you want to do this in your projects. You would say window inherits from two classes. And you can see none of them is actually interfaces. So we're doing something that's not exactly corresponding in Java. But since we talk about design, so that's okay. We want something powerful for modeling. So now we got window here, inherits from rectangle, and also inherit from tree. And then every node in the tree is actually a window, right? So that's why we're instantiating the G over here by window. Okay, I'll pause a little bit here to see if you got any questions. The next step for this slide here is to give you some sample code and trace that very quickly. Okay, let me read a question by Joy. To clarify, let's say in IFO, a class can only inherit from multiple classes if they are deferred. Similar to Java, in which a class can only inherit from multiple classes if they are interfaces. Okay, first of all, for the Java part, right? For Java, it can definitely if you want to, actually in Java, when you say inherits, usually you mean extends, right? Let me be precise over here. Let's say in Java. Okay, in Java here, if you want to implement multiple interfaces, yes, you can do it. You can say class C implements from two interfaces. On the other hand, when you say class C, you want to extend from two normal classes, either abstract or not, doesn't matter. So you want to say extends from C1, which may or may not be abstract, also C2, which may or may not be abstract, doesn't matter. You just cannot extend from multiple classes. Now, in IFO, what Joe said was actually correct. So now, if you want to inherit, when you say only inherits from multiple classes if they are deferred, no, that part is no. Okay, let me clarify this. Okay, the previous one is about Java. What about IFO? IFO, again, is more suitable for design. So whether the multiple inheritance can be supported not just on deferred classes, but also effective classes. Let me show you what I meant. Let me just draw something abstract for you. If I got class A over here, let's say it is deferred. And then I also got class B over here. Let's say that one actually is effective, right? You can see for some reason, there are at least one feature that's in A, for example, F, that's actually deferred. That's why it's a deferred class. On the other hand, all the feature A, B, C, D in class B, they're all effective, let's say. So now, if I have another class, let's call that my class. Okay, let's say my class is actually effective, let's say, for example, right? So now we talk about iPhone, okay, the language we're using for design. So now if I want to say inherits here and also inherits over here, and your question was, should it be the case that both A and B must be deferred in order for the multiple inheritance to be supported? No, it's not the case. So your parents for the multiple inheritance can either be deferred or effective, right? So there's no constraint on this side. So now when my class actually inherits from A deferred, in order for my class to be also in order for my class to be effective, so when you inherit from F into here, right, you can say F star into F here, it must be implemented. Otherwise, the my class will be deferred. On the other hand, for A, B, C, D, so A, B, C, D over here, so now you have choices. Either you can say, I want to inherit them verbatim. In that case, you don't need to change anything. Otherwise, I can say, I want to redefine those features. I can say A plus plus, plus plus, plus plus, and plus plus. Okay? Hopefully that answer your question about multiple inheritance. Okay, another question here. With regard to the name of the second parent's tree, okay, I'll talk about it. It seems more similar to a node than the whole tree. Am I misunderstanding? Okay, I see what you mean. I would say, yep, in some way you're right. So for this particular example here, I simply just say, maybe I could have said it's a tree node. Yeah, I just want to say it's a tree, and the way we represent a tree is by using the root of the tree. So if you feel like more understandable to rename this to be a node or tree node, that's okay too. Okay, I can see the confusion you have, but hopefully you see the idea over here. We're just saying for every tree node, we store window. Okay, no worries. Okay, we got one more question for Broderick. What happens if classes implement similarly named features and you inherit from both? That's a very good question. So I'm gonna see that in just a moment, right? You're talking about name clashes. We'll get there. It definitely should be handled properly. Okay, guys, one more show for this particular example here. Okay, I wouldn't just go too much into it, but I just want to show you what you can do when you actually want to work with like a tree structure objects. So for this one here, I'm just going to show you very quickly here, just an idea. What you really want to get used to is you want to build a tree-like objects. Okay, but how do you do that? Okay, so we got, let's say, without going too much into detail, I just want to give you intuition. Okay, let's say over here, let's say, well, I want to create W1. W1, 2, 3, 4, they're all window, so they can potentially be a tree, right? So if I create W1, so let's say it's a big one here, W1 over here, and also we got another one here, let's say W2. Let's say it's slightly smaller. Let me make it a little bit smaller. Okay, that's W2 over here, and also we got W3. Okay, it's a very small, let's say like that, and also we got another one, that's W4. Okay, so now creating individual objects is not an interesting bit. The interesting bit would be when you actually try to add things. For example, when you say W2.add W4, so what does that mean? For that one, that simply means W2, you're going to add W4, which is green. You're basically putting that into it. Okay, so, and then another one here, if you try to say W1.add W2, W1 is a pink one, add W2 and add orange one into it. So what you're doing is, you're basically saying, I'm trying to add this into this, right? Doesn't really fit, but you see my idea. And then finally, you are going to add W3, which is the blue, into W1. So what you're doing is, you're trying to add this one also into the pink one, okay? So this is kind of the tree operation you want to get used to, but we'll see more precise example later when we talk about the composite pattern. Okay, so hopefully everybody is okay. I did answer some questions there, but I would say this example is just to give you some idea that you can have multiple inheritance. So now, let me handle Broderick's question, which is exactly what I plan to have. Let's say this, okay? Also, I will show you some example, show you some table in the slides. Anyway, let's say this. every time you do multiple inheritance, you want to be careful with clashing variables, right? Let's say we have class A, we got class B. Let's say in class A, we already got a feature called foo. And for class B, we got another independent feature called foo as well. So the two foos have nothing to do with each other. And now, if we try to declare another class called C, syntactically, how do we do that? Let me show you on the slides first of all, right? If you see the slides over here, you can see we'll say class C inherits, and however, if you simply say this, okay, I'll switch back to the slide with a fix in just a moment. If you simply say class C, and then you say inherits A and also B. If you only say this, iPhone Studio is going to complain because somehow your foo inherited here, and also the foo inherited here, they actually got two foo over here. So you got name clashes. So how do we solve it? Idea is quite easy. You simply say, in order not to have this particular name clashes, rename one of them so that they become different names. For example, you might say, when I inherit this foo into here, rather than calling that as foo, I'm going to call that maybe far, for example, right? So that's kind of the idea. You just need to know the syntax to do that. Let me just go back to the slide example. Let's say we say class C inherits A, rename foo as fog, right? So the foo over here from A that's inherited to C, rename that as fog. And also the foo that's inherited from B, so now we call it zoo over here. Okay? So now let's see this. How do we actually understand the static type in terms of expectation? That's the final thing I want to go through before I go to the composite design. Okay, and then we can talk about it. Okay, what I would say is, let's talk about this table over here. Okay, actually, I'm just curious. I believe for all of you, you have the yes and no over there, right? For your Zoom. Let's see if this will work. I'm not too sure. Let's try. It could be a disaster if everybody tried to say yes or no, but let's try. So now let's say this. Let's say we declare object O statically of type A. Okay, and now I want to know whether each of these three will actually compile. Okay, that's what I want to see. So now, for example, if I say O the foo, should it compile? Yes or no? You want to try? I got 3 yes, 4 yes, 6, 8. Interesting. Yeah, that's good. It's good interaction. Good. Okay, it seems like the majority of you, 11, well, but you can participate later. But it seems like many of you think that should be yes. That's actually correct. Okay, let's try another one before I do illustration. What about O dot fog? Okay, O dot fog. This guy here. It seems like we got more people that's voting for no. Okay, it's actually correct. Okay, so now let's take a look. Okay, so now in order for me to illustrate this to you, let's see this. Okay, go back to iPad here. So now if you look at that, that's very good, guys. Thank you. Okay, so now you will rename the foo over here. Rename into, okay, so let me just make sure I got the name right. To fog. And also, over here, you rename the foo that's inherited into zoo. So now, the principle is easy. The rename only happened at the subclass level. So fog and also zoo, they only make sense to the compiler when you talk about class C over here. Okay? So now let's see the idea. Okay? So let's just give you two comparisons. If I say objects 1 of static type A versus object 2 of static type, let's say C over here, right? So now let's say this. If I say object 1 dot foo, if I say object 2 dot foo, and also if I say object 1 dot fog, and also if I say object 2 dot fog, okay, over here. So now let's say 1, and then 2, and then 3, and then 4. Let's just talk about these 4, and then the table will be something very similar. Okay. Okay, so now, how about we just choose one by one? Okay, just choose maybe, try. What about one here? Yes or no? Compilation. Okay, I got 6. Okay, 9 and then 10. Okay, seems to be more on the yes side. Okay, that's good. So this guy here should be yes, because object number 1, all you need to worry about is the static type. The static type for object number 1 is A. So what's defined in A? Just foo. Okay, so this is okay. So now it also proves that over here, if you look at number 2, over here, when you look at object 1, again, static type never changes, will just be A. So now, does A define fog? No. Okay? Fog is only making sense when you actually go down to the subclass over here. So that doesn't make sense, right? So now, similarly, so now let's do a final one, if you don't mind. What about number 3 over here? Should it compile? Yes or no? For number 3. So for number 3, the static type is actually, simply C. But if I say foo, should it be yes or no? Okay, good. So it seems like more people voted for no. In that case, yes, that's correct. It should be no. Because statically, for C, only fog makes sense. Only fog and also zoo actually makes sense. So now when you simply say foo, it doesn't make sense. But when you say fog, that's okay. Okay, so hopefully you get the idea for now. So the main idea is when you try to inherit from multiple classes for code reuse, you definitely are encouraged to do so if that makes modeling sense. However, you want to resolve name clashes when necessary. Okay, but if you got trouble later when writing the code, you can talk to me after during the office hour. Okay. Okay, that's about the multiple inheritance I would like to speak about. So now you got enough basis to actually talk about the composite. Okay. So now we want to talk about, don't forget the big picture, right? The big picture was, before we talk about, we want to solve this particular problem for the computer manufacturing, okay? Let's see how we can solve this problem here, okay? What I want to do is, at least today, I want to present to you the design, and then I might run a little bit over time, hopefully no more than, I'll definitely try to finish before 2:30, okay, definitely. This particular page, I would suggest we skip this page because that one summarizes the solution. I would suggest once we finish the composite pattern, we can revisit this page. Okay, let's skip this just for now. It wouldn't make too much sense before we talk about the different alternative design. Okay, so now what I want to present to you is the first design. And as a quick check for you, so before I present to you the first design, could you please just have a quick look of what the problem is very quickly, okay? And then I'm gonna present to you the first design, okay? I can switch back and forth. Again, you got some top level cabinets, you got some also subtree, root, chassis, and also you got some leaves over here, power supply or DVD room, etc., hard drive, etc., okay? So now, let me switch to my iPad here. So this is the first design. It could be good, or it could not be good, right? I don't know. We're gonna judge together, okay? So now let's look at the first design. Again, one technique I wish you can pick it up before you graduate from this course is you don't necessarily have to see the code in order to work out the design details. If I just give you a bond diagram, you can assume I draw the bond diagram very carefully. I show you all the necessary details you're gonna need. So just by looking at the bond diagram, could you please tell me if this design is going to work? Okay, let me go over it with you a little bit, and then we can have your input. You know, sometimes I even say, to really work out why alternative design is not good, is actually more important than the actual design, right? Because I think you want to really know the story about how to get to the good design eventually. But let's see. Let me go over the design with you. That's the first one, right? Let's say we got a client over here, and then we got a client-supply relationship. So the E here simply means equipment, which means in the client class, we declare some attributes of type equipment. So now you can see we have a top level equipment class, and it's deferred, okay? And then let's say there's only a single feature in the equipment, is called price, okay? Let's not worry about power consumption, just price and real number, okay? And then We also got another class over here called addChild. I'm not sure if you might draw some connection to the window example, right? Well, let me help you a little bit. Price is a little bit like X position, Y position, or width and heights. addChild is a little bit more like the tree operation, right? Well, you can already see this design may not be so promising for cohesion reason, right? But it's more to it. That's something I want to hear from you. But let's go on. I want you to really look at very carefully on the type of the variables I'm declaring over here and tell me what flaw you might find, okay? And then when I say addChild over here, I say equipments over here, which means I can add any equipments. I can add the disk drive as a child. I can add video card as a child. I can also add cabinet as a child, right? Any equipments, okay? So that's about the equipments class. And now I want to explain this guy here a little bit, the children, okay? Let me just say this. For this particular arrow here, it looks like a self loop, okay? It looks like self loop, true, but let's see why. If you have the class over here, let's say this. So I say class, deferred class actually, right? It's deferred, okay? Let me just erase this first, okay? Let me write it properly. Okay, let's say we say deferred class equipments. Okay, and then I want to explain to you what this arrow over here really means. Okay, somewhere in your equipments class, let's say feature over here, and then I will say children. You can think about the children is actually one of the tree related operation that we talk about. Let's say this guy here, let's say list, right? List of equipments. Okay, and then let's say this, and then I'm going to hopefully box it properly. Okay, that's our class over here. And then first of all, I hope you will agree, writing this in any OOP should really compile. Actually, you have seen this maybe in either your 2030 or in your 2011, right? Let me just tell you very quickly. Remember in your 2030 or 2011, when they talk about singly linked lists, for example, right? You would say you have a class called node. Sorry. Let me just erase this. So you will have a class called node over here, and then you will simply say node and the next, right? It's a self-referencing node, right? It's basically like a recursive data structure. And now we are indeed trying to define a tree, which is recursive data structure. So this referring to equipments over here should not be surprising to you, okay? I just want to draw your connection to the previous course. So now the question is, how do we understand this particular arrow over here, which does tells us something, okay? So now to really see this, let's think about this is the actual declaration in your equipments class. But now how do we draw that client-supplier relationship, right? So now if you think about it, if I look at this particular children, right? If you think about it, this is the name of the supplier. Supplier name. Because now the equipments, the context class is the clients. Right? Remember in the very first class back in the beginning of the semester, we talk about in the context of some declaration or method call, that will be the clients, and supplier will be whatever attributes you're using. Okay, so this will be client to be supplier name, and this will be the supplier type. Supplier type over here. Okay, so now funny enough, somehow the supplier is the same as the clients, which is completely okay if you got recursive data structure. So now the question is, how do we draw the diagram accordingly, right? So now let's see this. So now to draw this, let's say, for example, let's say you may want to show the detailed view for the class. So I will simply say equipments. Okay, equipment is a deferred class over here. And now what I want to do is I want to do a client-supplier relationship, right? When you do client-supplier relationship, arrow over here, remember the beginning end will be the clients. The ending end will be the supplier, right? Client-supplier. But now client-supplier, they are the same. So what you would do is from the client's equipment to the supplier, which is also a client, right? That's what you would draw. Okay. So now what about a label, right? For the label here, you would simply say children. That will be the name for the supplier, which is children over here. But what about a type, right? So you would say it's a list over here, but since I'm pointing to this equipment class already, so I can simply say ... Okay. If you simply put just equipments here, that's also considered as correct, but not as ideal because it's a duplicate of information. Whatever you're pointing to using the client supplier arrow should be the supplier type. So you don't need to repeat equipments here. You can just say ... Okay, hopefully everybody's okay with this error here. Okay, that's the very important part for the first design. Okay, so basically say for if every equipment there itself also contains an array or a linear collection of other equipments. Okay, keep that in mind. And now we only talk about the root of the hierarchy, right? And also we talk about disk drive, we talk about video card. So these are more like the base cases, right? You can think about these are more like the base. And then we also got composite components over here to say under this particular subclass hierarchy, this particular subtree. How about this? This particular subtree, we talk about recursive or subsystem. Okay, you got cabinets, you got chassis, you also got bus. Okay, hopefully everybody is okay with this second design. I'll try to run within another 10 minutes and then I'll finish the lecture. Okay. So now let's take a look at this. Okay, let me just give you a little bit more hints, and then I'll try to see if somebody can tell me what flaw you can see from the design. Okay, let me tell you this. Compilation-wise, we don't have any trouble. Okay, also I said you can also referring to yourself as a recursive data structure. It's not a problem either. Let me just go over lines of code with you to give you a little bit more hints. Let's say we declare chassis over here. We declare video card. We also declare disk over here. We can declare 3 variables. And then we simply create these 3. Okay, let me draw them very, very quickly. Let's say CH is a chassis. It's now pointing to chassis. Also, we got card over here. That's also pointing to some video card. And also, I'm running out of space. I'll put it here. So also D is pointing to disk. Okay, so these are the 3. Okay, we got CH, we got card, also we got disk. Okay, let's say this. Let's execute 2 lines conceptually. The first one, we say for the chassis, I'm going to add a child for the card, which means for the chassis, there will be, remember every equipment, you can see composite equipment is one kind of equipment. So which means the children will be inherited to the composite equipment, right? Inheritance. You can think about it a little bit more. But I can simply put children over here. And I want to say the first child for chassis will be a card. So that means you can point to this particular card. Okay, seems to be reasonable, right? I'm saying within a chassis, like a box, I have a card, video card. And similarly, I say for the same chassis over here, I want to add another child, which will be the disk. So now in this case, I'm adding a second child over here. And let me just use a different color to tell you it's a second child. The second child here is simply pointing to a disk over here. Okay, so now that's about my illustration over here. So now, can anybody tell me? So far, it seems like the first design is fine. But what about, is there any flaw I didn't really reveal? But there's definitely a flaw over there. Okay, I saw 2 of you already have some answer. Let me read them through. Okay, but for other of you, please take a moment to think about it, right? I will basically talk about what the issue is, and then, okay, let's see this. Okay. Okay, let me see. For Eto, you said the problem is only composite equipments can have children equipments. What you're saying is this particular children attributes or query should only belong to the composite equipment level. I'm pretty sure that's what you meant, right? I agree with you. That's the first part of the answer. Okay, I got another one here. You said disk drive and also, good. I'm glad I interpreted you well. You said disk drive and also video card will also be able to support children even though they shouldn't. That's good. Okay, I like the two answers. You basically talk about two parts. Let me go a little bit further. And what another one of you actually said, somehow this children feature will also be inherited to the two subclasses, disk drive and also video card. I agree with you. You're saying that they shouldn't be there for cohesion reason, number one. Okay, but I'm gonna show you something that's even more severe, right? So number one, children should not be in disk drive and also video card because of cohesion. I agree with you, but I would say there's something that's even more than cohesion. Okay, by allowing this particular design, you will have something that's going to be ridiculous to happen. Okay, I'll just show you one example, right? I'm going to write one line over here. Let's say this. So currently I got disk, I got video card, right? Can I say this? Disk D dot add child. And then let's say chassis. Or I can even make it more dramatic. Let's say this. I'll simply put, can I just put another variable here called cabinets? Right, cabinets is simply just over here. So now let's say, assuming that this has been initialized, so now I can say disk over here dot add child cabinets. You might think this is ridiculous. How can you do this? Actually, first of all, ask yourself, can this compile? Right? Let's figure that out. Static type for the context object here, the static type for D over here is simply just disk. Does the disk is simply disk. Does the disk drive, okay, disk drive over here, sorry, should be more careful. The static type for D is simply disk, which is a subclass of equipments. So now, does disk drive support add child? It does. So nothing wrong with calling this add child over here. And then we simply say, adding cabinets to a disk drive. Can you do it? Maybe not, right? So now basically the problem for the first design is, number one, it's about cohesion. And number two, also the children should be put inside the composite equipment. And number three, if you allow this design to happen, you're gonna get something very ridiculous like over here. So now, for example, if later on we give you this particular design, you should really tell us this is what you can do, which is ridiculous, right? So now this will allow us to say, in the disk, there might be another children over here, and then you say the first child will simply point to some cabinets, right? Some cabinets is simply pointing to some cabinets. Okay, so that's about the first design. Okay, hopefully everybody's okay, right? That's good. We still got 45 people here, so that's nice. Okay. Okay, let me just summarize very quickly. I know I'm running over time. I do appreciate you stay here, but let me just talk about what's going to happen. Okay. Basically, we talk about the very first design for the composite. Okay, and then the next time we're going to finish about the second design, which is the real composite pattern, and then, okay, let me just answer a quick question. You're asking about, are we assuming that there's a create cap make? Yes, we assume that. Yes, we're assuming that for every class over here, including the cabinets, every class, we do have a make feature. Yes, we do. Yes, indeed. So now, next time, we're going to finish the composite pattern, and then we'll actually go on to the visitor pattern. Okay? And then, so I would say before next time, please review all the notes. You will see also the design diagram on the lectures page, and also the slides, and also review the state pattern. Okay, so if you any questions before I end the session, I will publish the recording later today. Okay? Everything has been recorded, so you don't have to worry. Okay, any questions? I'm willing to take more questions if you have. Anybody? Okay, hopefully this time it works well. So maybe, yeah, just post your question here as I go through the lecture, or you can ask me during the office hour. Okay, thank you for coming. I will see you on Wednesday, the same time. Okay, bye-bye.